So optimization. We're talking about optimization. We are basically dealing with just applied minimums and maximums. That's ultimately what it comes up to. It's a min-max problem where I'm either interested in a maximum something or a minimum something, and here's a context to it, and we move on. You have actually been doing optimization problems since Algebra 1. This would be an example of an optimization question that would have come from Algebra 1 that you should be able to do from Algebra 1 knowledge only. So let's talk about that so that you can not look at me like I have 7 heads and think that I'm a liar. All right? So when I'm dealing with these problems, there are going to be, the examples I'm going to show you are going to be geometric problems. I can't quite show you the questions where that's not the case because we're going to need to have some integration and some rules from that anti-differentiation and things like that. And we're not quite there. We'll actually be there starting Monday next week. So, we have a rectangular area to be enclosed by a wall on one side and fencing on the other 3. So essentially what we're doing is we are looking at a situation where I've got myself a wall. Look at it. Isn't that a great wall? It's the best wall ever. This wall is going to be huge. It's going to be huge. All right, there's my wall. On that wall there are going to be 3 sides that are going to be made up of fencing. It is a rectangular area that's been created. I should probably label this particular rectangle or these sides. What are we going to label these sides? Yes, yes, and yes. That is not going to work. You can label 2 yes, but you can't have them all be yeses. So we know this is equal to this, and these are going to be, this can be different. So you want to call this X? No. Sure. Oz has made a decision. Good job, Waldo. We've got this. Now, what I want to do is I've drawn my picture. I've labeled my picture. We are ready to start working now. First thing we need to do is we need to come up using these variables. We need to come up with usually 2 equations. The first equation is the equation that I actually want to optimize. So when I read through this question, it says, what is the maximum area that can be enclosed? I want to maximize my area, which is the length times the width. Now here's a problem. I have 3 variables, and I really want to only deal with this question as 2. So what's going to happen is there are going to be secondary equations that we're going to utilize. And those secondary equations are equations that exist to reduce the number of variables in my problem from 3, 4, 5, 6 down to, hopefully, 2, an independent and a dependent. So as I look through this question, what other information did they give me? I have 24 feet of fencing to be used. So I know that I have 24 feet of fencing, and that's going to make up what? The perimeter, which would be what? 2L plus a single W in this problem, because we're not going to have 2 W's, we're just going to have the 1 because we're using a wall to assist us. Yay, walls. It's the only time a wall is useful. So we've got all of this. We're ready to go. We can actually start working with some of what we've got. I'm looking at this. I want to know maximum area. So what I'm going to do is I'm going to realize that 24 minus 2L is W. And the reason why I did that is A, W is a whole lot easier to solve for than L. And now that I have this, I can actually write an equation for A such that it's in 2 variables, length and area. Or simplifying that down a little bit, 24L minus 2L squared. Now, got this equation. This is where Algebra 1 comes in. I want to find the maximum area. What would you have done with your calculator? What do you mean by plug them in? You're going to really plug in all possible numbers? Every number ever. Go. We would take our calculator, we would plug into y equals. That would create a graph, and I would simply look for when is the area going to be the highest point, right? And that's what we would do. We don't have a calculator. So what do? Well, we're trying to find a maximum, and a maximum happens when we've reached, if we're thinking about what this graph would look like, it would come up and it would be a downward-facing parabola. We just need to figure out where the derivative equals 0. That would give us our critical value, which would then tell us that that's a relative max, and if we can prove it's the only crit value, we're good to go. So I'm going to take a derivative. Now here's where things get a little weird. I'm going to take the derivative of this function. I'm going to take the derivative with respect to the independent variable. In this problem, my independent variable is the length. So I'm going to take the dl of the problem. S and Q. I hate Q's. So I want the dl of 24 minus 4L, and we want to set that equal to 0, which means L must equal 6. Not bad. Now I do want to make a point here. I am actually going to put a limit on this. Can my L ever be a negative number? Length cannot be negative, therefore we want to say that. And that's a really useful thing because technically we might wind up with critical values that are really weird. So I'm going to look at this ray from 0 to 6. If I select a number less than 6, between 0 and 6, what type of a value will dl give me? Give me a positive, and then we will get a negative. Agreed? So my first question is, at 6, is that a relative max or a relative min? That is a relative max. Also, how many crit points exist? So what can you tell me about this relative max? That's my absolute max. Yes, question. When I decided the signs? That's dl. So whatever I wind up, when I solve this for 0, whatever values I am using here, or sorry, let me think how I want to say this. Whatever equation I got this value from is the equation that I subbed back into to come up with this sign chart. Does that help? So when L equals 6, that gives you dl, which is 0. Yes. Bingo. That's where we have a slope that, if we look at the actual a function, a is going to increase up to 6, and then at 6, it's going to start to decrease. This is where things get fun. We have to make sure that people are 100% convinced that this is, in fact, a maximum. So we say something like the area, or the max area, is at L equals 6 feet. But then we have to defend that. Since L equals 6 feet is the only crit value, and the ADL changes from positive to negative at L equals 6 feet. What did I do? First thing I did is I made my statement. So this is my conjecture. Maximum area is at L equals 6 feet. And then this is my defense to that. I had to state that L is the only critical value, and I had to show that dA dL changed from a positive to a negative. So I've shown you that's a relative max, and I've shown you that it's the only critical value, making this a maximum area. Have I answered the question yet? No. Question asks, what is the maximum area that is enclosed? I've defended that when L is 6, we have a max area, but I haven't answered the question. I have to find out what the area is. So how do I do that? We can do a couple things. We can substitute into 24 minus 2L to get W if we want to do that. Or I can sub it into A is equal to L times 24 minus 2L. Which one do you want to do? Okay. If you want to do the first one, you can, but I can also do A evaluated when L is equal to 6 is going to be 6 times 24 minus 2 times 6, which is 24 minus 12 is 12, and 12 times 6 is? Huge. Cool. Questions on that? Good question. I like that. Not bad. I can accept that. A 6 by 12. It's not terrible. Let's move on. Slightly different problem. I now have a manufacturer who wants to design an open-top box. Has a square base. It's allowed to have a surface area of 108 square inches. Apparently that's all they have to make the box. So don't screw this up. What dimensions will produce the box with a maximum volume? Step 1, draw a pretty picture. So I have my box. You ready for this? It is an open top box. I speak weird words. I don't know how I feel about that. I think Walt is lying to me. So far, so good? We should label this box. I didn't say name the box, I said label the box. Maybe you do. SS and S is close. I would probably call this S and S and H. Why is it SS and then H? Side side because the base itself is square and we have no clue what the height's supposed to be. Maybe it'll be the same thing as the square. And then we'd be really happy about this, but we don't know. We need two equations. We need to know, first off, what am I trying to maximize or minimize? Trying to maximize volume, so let's talk about that. Volume is what? Base area times height, so base area is S squared times the height. Again, I'm down to 3 variables. I'd really like that to be 2. So I should probably come up with a way to make my 3-variable problem a 2-variable. What's going to be my connecting equation? Surface area. I know my surface area is 108, but how do you find the surface area of an open-topped box? HS. Or I like to put 4SH because then it gets to be Forsh. Just sounds cool to be able to. S4H. S4. Alright. Now, for those of you who didn't catch that, you have one base, which is S squared, and then I have 4 different sides, and every single one of those is going to be S times H, so 4 times S, H. Cool. That's an excellent question. So when I'm talking about surface area, we're talking about the materials being used, and we're going to measure that on one side. You're the second person to ask that question. I'm just not going to ask. I'm going to hope that he keeps the question simple. Remember, this is a class that we firmly believe in KISS. Keep it simple, students. I'm on record. I should say it the right way. All right, ladies and gentlemen. I should probably turn V is equal to S squared H into just a single variable. What am I going to solve for in 108 equals S squared plus 4SH? Want to solve for H? H is the correct thing to solve for. I will have some student who usually comes up with a really bright idea. It's the same idea I came up with that then fails miserably. They go, solve for S squared. That'd make life really easy. What's the problem with solving for S squared? No, when I say S squared, I really just want S squared equals. I'm still going to have an S in the problem, and I didn't get rid of I changed it into a single variable. You can do that sometimes where, like, if this could just be, if this wasn't an SH and it was just 4H, and we moved that, then any time I see an S squared, I can just change that out. But I don't have that, so what is H going to equal? Is it 108 minus S squared over force? Groovy. We're ready. We can start doing this problem. Our volume is S squared times 108 minus S squared over 4S. And this is where knowing how to simplify is really, 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 really useful. That's terrifyingly gross, isn't it? But if I multiply this, do you agree that this S would get rid of one of these S's? So could I rewrite this? 108S minus S to the third over 4. And if I really wanted to be fancy about this, I could call this 1/4 times 108S minus S cubed, just so I don't have to deal with the fraction. Take the derivative with respect to the independent variable, which is what? So now we're looking at dV/ds. Please do not ever use a dt. Be careful to know when you're using a dt or not. Am I really interested to how this volume is changing with respect to time? I'm worried about the volume with respect to whatever my side length is. And I want that to change from an increasing to a decreasing. So that's why it's dds. So we go dV ds is equal to, and we take the derivative. Which turns out to be something fairly simple. And after we find the derivative, we set that equal to 0. Trying to find a critical value. What does this have to equal? Plus or minus 6. And let's be smart about that, because really, if we think about the limits for S, S definitely has to be bigger than 0. So really, I just want S to equal 6. Because minus 6 is extraneous. Look, we've got a 6 again. That's cool. If we select a value between 0 and 6, our dV/ds is going to be Once we cross, will become a negative value. What does that tell me? That's an absolute max. How do I know? Max volume is at S equals 6 inches since S equals 6 inches is the only crit value, and dVds changes from plus to minus at x equals 6 inches. Again, your statement, I have to tell you that it's the only crit value. I have to tell you that it changes from positive to negative for this to be a max volume. Have I answered the question? What do I do? Plug 6 in where? Are you sure? Can't plug it into the OG. Which OG equation? Huh? I just need the height. Why? Yeah, it's the only dimension I need. I already have I already have S. (108 minus S 6 squared is 36 divided by 4 times 6. I believe the answer is 3 inches. So in this problem, S equals 6 inches, H equals no, you can. When you said OG, I'm assuming you mean the 108. What was your volume? Oh, coinky dink. Now that, but that is something to be, So why are we not subbing it in there? Now we could have subbed it into our secondary equation. It's totally what you did. They probably would have definitely been trying to figure out why you used that equation there, but what they're looking for typically, I would say I would probably expect to lose a point because you did something clearly wrong, but you would probably get all the rest of the points. And really think about that. What are they going to look for? They're going to look for, did you take the derivative? Did you come up with an equation and did you take its derivative? Definitely. Did you find the critical point? Definitely. Did you defend that that has to be an absolute maximum there? Definitely. So the only point you could really lose is the answer point, which is usually only worth 1 anyways. So you would have gotten out of maybe a 3 to 4 point question, 2 to 3 of the points, even though you made a terrible mistake at the very end. What? I never took the derivative of 108. Oh, you're talking about here? Because that wasn't a 108, that's a 108S. Because the first thing I realized is that this is just going to be an S times 108 minus S squared over 4. And then when I distributed my S into the problem, 108 has an S. Now I'm up to an S cubed. All right, one more. Volume of a cylindrical tin can with a top and a bottom. A cylindrical tin can with a top and a bottom. Cylindrical tin cans have 2 dimensions, a radius and a height. I know that the volume of that cylindrical tin can with the top and the bottom has to be exactly 16 pi cubic inches. Why? Because that's what makes the question easy. If minimum amount of tin is to be used to construct the can, what must be the height in inches of the can? So what's going to be, we're going to minimize or maximize, in this case minimize surface area. Please do not call it SA. Call it S, call it A, but do not call it SA. We do not need compound variables in this problem. I'm going to call it S, surface area. Big S, there you go. What is the surface area of a cylinder? Two pi r(h) is the circumference times the height. If we were to cut that and roll it out, that would create a rectangle of 2 pi r times h. And then we are going to have pi r squared for each of the bases, so that's double the 2 pi r squared. We want to minimize that. Cool. Utilizing the fact that the volume, 16 pi, is going to be our pi r squared h. Which, by the way, is the area of a circle, which is inches squared times the height, which turns it into inches cubed. Good times. Unit analysis, it is your friend. What do we do? Solve for h. I like solving for h because I don't want to have any square roots in my problem. Seems fair? Solve for h. What does that become? These pi's will divide out. I get 16 over r squared is h. So let's substitute. S is equal to 2 pi r 16 over r squared plus 2 pi r squared. I should probably rewrite that. Let's call this 32 pi over r plus 2 pi r squared. Cool. Take the derivative. What is my independent variable? Fantastic. So I want ds dr is now I just have to figure out how to solve that. By the way, what do we know about r? We really don't want an r that's equal to 0 because then we don't have a cylinder. You have a stick. Not very useful. It has height, but it doesn't have radius. A radiusless stick. Of course. This is my infinitely tall stick, so I can have 16 pi volume. This is what I love about calculus class. Nothing makes sense. All right. What does r have to be? What does r have to be for negative 32 pi over r squared plus 4 pi r equals 0? Zero is a critical value. We did omit that r can equal 0 because we don't want to, as you stated earlier, we don't want an infinitely tall height. And so that's not going to work out, so we want to find when r is 0. So you got 2. How'd you get it? Okay. Whoa! Whoa, Nelly. That makes me feel better. So r cubed had to be 8. So r must be if we have a number between 0 and 2, then this becomes negative 30, let's sub in a 1. This becomes negative 32 pi plus 4 pi. That's definitely a negative. And then it will change into a positive, which means what? We have a minimum surface area at r equals 2 inches. Since r equals 2 inches is the, you haven't caught that this is pretty much the same thing every time, critical value, and dsdr changes from negative to positive at r equals 2 inches. Cool, I've now proven that the minimum surface area exists there. Have I answered the question? That would have been bad. It wasn't, but it could have been. What's the height? To the non-OG equation. All right, you are going to have an assignment. You have the other 2 problems at your homework assignment, but we're not going to start those 2 problems. I'm going to let you do those at home because I need to move on. Go to the next set of notes. We're not going to finish this today, so you're not going to be asked questions about it, but I want to start off linear approximation. If you have not been able to find this equation of a tangent line, you better figure it out. What are you doing, Shiv? Put it away. Kivon. So, if you cannot find the equation of a linear tangent line, or a tangent line specifically, you are going to wind up suffering horribly during these next couple of days. You need to be able to find the derivative at a point. You need to be able to find the point on that curve, and you need to be able to create that tangent line. What we're going to do is realize that sometimes it's easier to come up with the answer on a tangent line that's close to the answer. If I'm looking at just the graphic down here, if you look between these 2 values, you'll notice the tangent line and the curve are really, well, they touch at A, right? But you'll notice that they look like they are really close to each other between those values, agreed? That is not on accident. In fact, if you take a curve, all right, and I will, actually, let me show that real quick. I have a cool visual for this. If I were to take a curve, in this case, let's call this curve, what do you want to call this curve? No, don't give me a name. J of x equals, all right, let's come up with an equation for Jerry. 25x, this is boring, to the 5th power cosine, whoa, that's cool, cosine of x. That's pretty cool. Plus 23, no, we're not going to do anything else. All right, here's what's going to happen. I'm going to zoom in on this particular part. Now that still definitely looks like a curve. Let's focus in on this where it looks really like a curve. You agree that still looks like a curve? How about now? What does that look like? That is definitely what looks a lot like a line. I've zoomed in so close that my curve has become a line. You have to realize in calculus, one of the best powers of calculus is the realization that the answer is not the, typically we're not interested in the exact answer, we just want the answer that's close enough. If you are going into engineering, that is going to be one of your biggest answers. Look, I don't have to have the exact answer, I just have to be close enough. That's right. Well, no, you have to draw a curve. If you wanted it to be a line, then you just keep zooming in until it becomes a line. It's what's called local linearity. The idea of using, it's called local linearity. When I zoom in really close and I look at the local section of it, it looks like a line. So, this concept of local linearity. Actually, I have to come back and go back. There we go. What we're talking about, this is going to be called a linear approximation or a tangent line approximation. I'm going to use those interchangeably. You need to be aware of that. Okay, if I'm ever talking about an approximation and a line, I'm talking about this linear approximation idea. The other thing that I do need to know, because it's really important, is whether my linear approximation is an over or an underestimate. And that has to deal with how the curve works. Okay? If I have a function that is curved like this, what can you tell me about this particular, both of these curves? Well, what can you tell me about the curve itself? Both of these are concave up curves. Do you agree? Now, an interesting thing happens when I look at these curves. When I look at these curves, this tangent line is somewhere specific on these particular concave up curves. Where do you notice the tangent line is? Or put another way, the tangent line is these are definitely not parallel to the curve. They're definitely not perpendicular to the curve. Under. Look at every single one of these lines. This is always under the curve, right? In that case, we would say that our linear approximation has a underestimate. By the way, when is something concave up? F prime is increasing or is positive. On the flip side, if we have a concave down function, which means F prime is decreasing or F double prime is less than 0, what do you notice about the tan lines? Above. This becomes extremely useful when we're trying to come up with an answer and knowing, okay, was I close? Yes, but how was it off? If I have to wind up fudging the number a little bit, I come up with that. I put stars next to the statement below these curves. That's really, really, really important. What we have done in the past, so we've talked about F double prime at a point, or we've talked about F double prime as the whole region. We found entire regions where we're concave up and concave down. We've also talked about evaluating the concavity of the second derivative of a function at a specific value where the critical point is. We're no longer going to be doing that. What we want to do is we want to make sure that the region between the point and my evaluation point, let's call this just f of x, call this x, f of x. If I look at this point and that point, I want to look at the region between and make sure that the concavity stays the same between a and x there. It's kind of weird when you talk about that. I'm going to look at the first example, and then from there, hopefully that will make a little bit more sense. So flip this over. We're going to try to take out this first example. Hopefully we'll get through that before the bell rings. We should. It's not terrible. First thing I would like you to do is I would like you to write the equation of a tangent line of the graph f at the point where x is equal to 3. I need a point. How do I find a point? What do I have to figure out? 9 times what? I also need to find f prime of 3. But to find f prime of 3, I should probably find... Now, I don't know about you, but I really don't want to do f prime of x right now because that's a... Well, why don't I just make it so it's not a product rule? This is 12x squared plus 2x. And I would probably still factor a 2x out of that. The reason is that that's going to make my life a whole lot easier. 2 times 3 is 6. Or if my board decides suddenly it doesn't want to write, 6 times 18, 19. So what's 6 times 19? 114. So my equation of the tangent line is y minus 117 equals 114 times x minus 3. This is one of the few times you're going to see me modify this. Modify. I'm going to call this y equals 114 x minus 3 plus 117. And you're going to see why that's important now. Part B says, using the equation found in Part A, approximate 2.97. So I'm trying to figure out what is f of 2.97. I do not, under any circumstance, want to have to do 2.97 squared times 4 times 2.97 plus 1. So what I can say is that this is approximately, because 2.97, how close is that to 3? It's pretty close. So what I'm going to do is I'm going to do this. 114 times 2.97 minus 3 plus 117, or 114 times 0.03. Because what I've said is that y is approximately this, and then I can sub in a 2.97 into the x, and because it's close to 3, I'm going to get a near answer. I'd like you to figure out what that value is. We'll talk about C tomorrow.